In this video, we're going to look at Section 4, the Taylor polynomial question from the 2017 December exam for Math 121. Our first step is to construct the second-degree Taylor polynomial for a particular function, and this is essentially a process question. So we have our function, which is ln of 3x, and if we're going to construct the second-degree Taylor polynomial, we need to know the first derivative, which will be 1 over 3x and times the derivative of the inside. That's 3. And that maybe surprisingly simplifies down to 1 over x. It actually isn't that much of a surprise because we can rewrite this using log rules as ln of 3 plus ln of x. And so we see the derivative of that would also give us 1 over x. If you use the original function, that's fine. Just be careful when you simplify it. You will get something relatively straightforward. And then for the second derivative, it might be helpful to write this as x to the negative 1. Then we can use the power rule, negative x to the negative 2, which is negative 1 over x squared. Next up, we evaluate this at the point x equals 1. F of 1 is ln of 3 times 1. That's just ln of 3. F prime of 1 is going to be 1 over 1, that's 1, and F double prime of 1 is going to be negative 1 over 1 squared, or negative 1. And then we simply remember our formula for the Taylor polynomial of degree 2. It's the extension of our linearization. We have the value, ln of 3, plus the slope, which is 1, times the x value with the shift from x equals 1, and then we have the second derivative over 2 times the quadratic term. So this is just paralleling our f of a, f prime of a slope times x minus a, f double prime of a all over 2 times x minus a all squared. That's the generic form, and this is the particular form for us. And we're going to be using this momentarily, so I think it's helpful to just tidy this up a bit and just be clear about where the parentheses and such things are. There we go. So we'll just tidy that up. Because in part B, we're asked to evaluate a limit as x approaches 1. And we can see that there's some interaction between the things that we have in our Taylor polynomial, the ln of 3x here. Right now we can't cancel anything. If you want to use L'Hopital's rule, you can try that as well. But I think the easiest thing to do is use the approximation that ln of 3x is equal to ln of 3 plus x minus 1 plus, or negative, minus 1/2. Minus 1/2 x minus 1 squared. That's coming directly from this expression over here. And because we're doing a limit, this approximation is most accurate as x approaches 1. In fact, this approaches equality exactly at the limit we're trying to evaluate here, which is as x approaches 1. So some fancy theory going on behind that, but at the end of the day, the approximation is perfect when x is equal to 1. It gets better and better as we approach 1. So this substitution is a valid and helpful one. So what we're going to do is replace our ln of 3x with this expression here. So ln of 3 plus x minus 1 minus 1/2 x minus 1 all squared. That's the term we just substituted out for, minus ln of 3 all over 1 minus x. Of course, we get some things canceling now. That's what makes it interesting. And when we get done this, we're going to have the limit as x approaches 1 of, let's break this into individual terms. X minus 1 over 1 minus x minus 1/2 x minus 1 all squared over 1 minus x. Now there's a little bit of a tweak we can make here There's a few different ways to do it. Just a little side note here, a different color. 1 minus x is the same as, if I multiply that by -1, minus 1 plus x, but I can't just multiply things by -1. I have to multiply by 2 -1s is the same, or if another way to write this is negative x minus 1. Another way to do it is maybe factoring out the negative. Here we bring the negative out front, we get just x, and I factor a negative out of the positive one, I get a -1. At the end of the day, that lets me replace this denominator here with exactly what's in the numerator. And when we do that, it allows us to cancel things, like so. We're asking for the limit as x approaches 1 of, get back here, there we go, x minus 1 over x minus 1, well that's just minus 1, minus a half x minus 1 squared, oh sorry, and then, yeah, we have a negative sign there. We have negative a half x minus 1 on top is left, and with another negative sign out front of that. As it turns out, we don't have to be too careful about that, because as we evaluate the limit, and as we use values closer and closer to that point, and as x approaches 1, what we're going to have are values in this term that approach 0. So we're actually going to get -1 minus plus a half, technically, with a double negative, but the key thing is plus 0. And we're going to end up with a value simply of -1. And the solutions that are posted online also have the L'Hopital's rule approach. Either way is fine, as indicated in the question. I think it makes some sense, given all the hard work we put into the first part, to take advantage of our Taylor polynomial in part 2, though, in part B here.